Is it audible? Okay, I think the audio is working. Let's get started then. Welcome back to the Blaze stream. I had finished, last time I had finished creating a texture manager that handled textures, so the creation and destruction of textures, and it returns you an ID, right? And the whole goal for that particular system is to start using bindless textures. We haven't covered what bindless textures are yet, but we'll get to that in a second. 1 second. This is a simple, easy problem to solve. So just amend that commit. All right. So we have texture IDs that are being returned by the system. So that is fine. We currently have these fetch image and fetch image view, which has to be deprecated eventually. And we have the rest of the things that are known. So what we have to do now is to get a descriptor set that can handle multiple different textures in a single set. So instead of using a descriptor location where we'll put one texture and then swapping out the descriptors at that location, we will just have a single descriptor that will stay bound forever, that will have every single texture that we need. So let's get started with that, right? First things first, we need to create the set descriptor set. So what do we need for that? First thing, we need a descriptor set layout. But unlike the previous descriptor set layout, which was created alongside the pipeline, this set layout is entirely a property of the bindless system itself. So descriptor set layout, okay, M set layout. So this is something that belongs to the bindless set. Bindless descriptor info. And this is texture manager. So let's get to it. There'll be a descriptor set layout. We'll need a descriptor pool. Even if the descriptor pool is only used to create a single entity, we need it. Descriptor pool, better. Let's give it full names, right? Descriptor set layout there. And finally, the descriptor set itself. Now, currently we're using a single descriptor set. We might need to have multiple descriptor sets for each frame. So one per frame. But for now, we don't particularly care. So these three things we have to initialize. Okay. And that we will do in descriptor set create here. But we'll have to take these in through the constructor. So one of the things is sure, which is descriptor set allocation will not fail, right? So we'll come to that in a second, but we will take descriptor set layout. So set layout. We will take VK descriptor pool. So that's pool. And we should be able to get it working with just this much. One thing I will check to confirm is VK create descriptor pool. So VK create descriptor pool. And let's see if it actually throws any interesting errors. So out of host memory, out of device memory, and fragmentation. Okay. That's an extension error. Let's check what that is. Descriptor pool creation has failed due to fragmentation. Descriptor pool creation has failed due to fragmentation. Okay, that's all that was. So none of these are proper failures, let's say. None of them will actually occur in our system in a way that is recoverable. So if host memory, we're out of host memory, we can't do anything. And it wouldn't happen on a desktop system because we have virtual memory. Out of device memory, again, if you run out of device memory, nothing we can do because if there is no space on the GPU, recovering doesn't help us do anything. Ideally, this descriptor pool will be created, not ideally, but actually this descriptor pool will be created ahead of time. So again, the pool can also be created within the constructor, and probably that will be the same thing with the set layout itself. So let's look at that too. VK descriptor set layout, VK descriptor set layout. There's a create descriptor set layout right there. So what can it return as a return code? Out of host memory, out of device memory. Again, non-recoverable. So we can leave this consistent with what was. Okay. Did we actually use any constructors that consume? So we can device create. These can actually fail, but render device creation failure is fine for us because, we can have an alternate render device or something. Texture manager is a dependent inside render device creation. So failing to create texture manager can be considered a failure. Fine. We will make it non-trivial. So we create descriptor set layout, we create descriptor pool, and we can also take VK descriptor set, descriptor set. That's better than just calling it a set. All right. So with that, what we can do is we can say, folks have got implemented. Put there, check this, create the declaration, and just cut. Let's create texture. The space there. Texture manager. I paste right there. So far, so good. We just need to add the remaining. So M descriptor set layout gets the set layout. M descriptor pool gets the pool. M descriptor. Yeah, normally I do one live stream a day, but yesterday I ended up doing two because I had some time and I thought, hey, let's get ahead with this. The main goal of my live streams is for me to just, have a consistent use of time, let's say, to make sure I don't do anything that's superfluous. But I want to make progress, so I don't really have to necessarily have to wait for everyone. Though it is one of the ideas that I won't overdo it. I won't do too much. But anyway, descriptor set, layout. So let's create that. So we create descriptor set layout, create info. And what we can do is we can actually just go in the misc data where we created the descriptor set. We can copy this whole thing. Per material binding, per frame descriptor set layout, whatever. We don't care which it is. We just want to get it, right? We get it like this. And we can start adding things here. So render device, per frame descriptor binding doesn't exist. So this is just descriptor binding. This is descriptor binding. Where we can call it the whole name. So whole name it is. It won't be called expression anymore because of a little reason I will get through in a second. Okay. So we said descriptor count is 1 in descriptor set layout binding, but in reality, the count will be the capacity of the texture manager now. So descriptor count will be capacity. Max count. We took it as max count. So effectively, all the textures that are in memory will all be bound to the shader for usage. That's the idea here. So binding count is 1, but within that binding, there is a lot of descriptors. So this is just descriptor set layout. Why not? This is, again, descriptor set layout create info. So how did I learn C++? Well, I started with C, used the Kernighan and Ritchie ANSI book. So C second edition. And you see this one? Went through this book from front to back, did everything. Good place to learn C. Once you learn C, then you can start adding C++ concepts one by one, right? So you can slowly add features as you go, let's say. So now that takes care of this descriptor set layout. And then practice, a lot of practice. You have to practice. Like at the end of the day, this is a skill, and all skills need practicing. I've been doing C++ for, I believe, 13 years now, 14 years. So yeah, comes with time. Why are you doing Vulkan when you can do OpenGL? So one, OpenGL is simpler, but it's also less efficient. Vulkan gives me a lot more control. Second, OpenGL doesn't get all the new features. It's kind of stabilized at 4.6 and it will never really get any upgrades because the new thing is Vulkan, right? It's just like DirectX 11 doesn't get upgrades. People use DirectX 12 now. 12 is just like Vulkan. 11 is similar to OpenGL, but closer to the new things. And so Vulkan, to learn, it's better to do OpenGL because it takes away all of this, internal details like descriptor set and stuff. But once you know how to do graphics, Vulkan allows you to do a lot more interesting things, like bindless rendering, for example. In OpenGL, this is difficult. In Vulkan, this is just as simple as changing the number of objects here. So, yeah. Descriptor set layout. Also, the debugging in Vulkan is much better than OpenGL. Okay. So, descriptor set layout happened here. So, we've created that. Let's look at the next step, which is to create a descriptor pool. So descriptor pool. And again, let's recreate descriptor pool, create info. Descriptor pool, create info. Designate initialize this, recreate structure, type, descriptor pool, create info. Pnox is null pointer, flags is 0, max set is max count. So how many sets? Actually, no. Correction. Max set is exactly 1. Pool size count is 1 and it will have a single pool size. So single pool size. Okay. And then we will add the pool sizes here. So we create descriptor pool size. Pool size equals so type is combined, not combined image sampler necessarily, because again, there's a little thing with this. OpenGL first. Unquestionably OpenGL first. Vulkan is difficult to do without knowing the concepts of graphics. OpenGL, learn the graphics concepts. So you learn OpenGL. So you learn how to do graphics with OpenGL. Once you finish that, move to Vulkan. You'll realize the difference because like the triangle in OpenGL is, I think, around 150 lines. The triangle in Vulkan is around 1000 lines. So anyway, coming back, pool size. So I wasn't sure of which type of pool to use, but I think I'm going to go with combined image sampler. Descriptor count will be max count. So we will create as many pools as we might need. So, sorry, we will create as many textures worth of space as we might need. So that allows, yeah, I mean, look at how many streams, episodes I had to do before we got to Triangle in Vulkan. And that is me after having known the Vulkan API to a certain extent. A well-known statement in computer graphics is there are 3 steps to learning computer graphics. Make a triangle, make a textured cube, and then do everything else. Our descriptor pool is set up. We need to do a weak check on this. Descriptor pool goes there. Last thing, descriptor set. So we can just type that and then remove this. VK descriptor set. VK allocate descriptor sets. It takes a render device, allocate info, so descriptor set, allocate info, and takes the descriptor set here. Okay. Then VK descriptor set, allocate info, const, descriptor set, allocate info equals this. There we go. Next is null. Descriptor pool is the descriptor pool. Descriptor set count is a single set. Set layout says descriptor set layout. Formatted, we can check on allocate. And finally, descriptor set is already added textures, texture manager. So what is happening now? This whole thing is created. One thing, I will move the allocation for the texture manager right before the texture manager, isn't it? That way we don't have to clear it up if there are any issues. Okay. So this creates all the descriptor set and everything we need for texture manager. And with that, we are done with the initial part, let's say. However, combined image sampler is not the only type of texture we use. There's another one known as storage textures, which I'm not taking into account at the moment. We'll come back and write that later because currently we're not using it. Okay, so that's texture manager create. It has created everything. This is done. So what happens next? These descriptor sets will be assigned to in the constructor, but they're never used after that point. In order to use them, when we create the texture, so when we do a create texture right there, once we create it, we will commit it. Okay. So how do we commit it? After the texture has been created, we have the index. Index also means we'll have an inner index to it. So we'll take the inner index from the index. So UM32T inner index equals index and index mask. So that gives us the inner index. And yeah, that's so for now, that's kind of all the word from the inner index. We then will do a VK descript. So we can update descriptor sets. So we have, I think, render device dot device, descriptor write count, a single write, descriptor writes, descriptor. So that is single descriptor write, and no copies. Okay. So with this, we just need to create that descriptor right here. So VK descriptor right, which is right descriptor set const descriptor, right? It is this. I think we have one of these inside miscellaneous data as well. We can just check for that, right? Descriptor set like there. So we copy this texture manager and paste it right there. Okay. The descriptor set will be m descriptor set, descriptor buffer info. So these will change. We will instead have vk descriptor type combined limit sampler. Array element will actually be the inner index. And descriptor buffer info will be just null pointer because this is not a buffer, this is an image. So we have to write the image info. So vk descriptor image info. Sampler is, we don't have it right now. Image view is the image view we have created for this. So that is texture view. Image layout is vk image layout. Okay, hold on. Let's check the image layout. Initial layout is image layout undefined. That obviously this would not have. So we say image layout shader read only optimal. This is an assumption here, straight up an assumption that we will have the given texture in shader read only optimal when we get to that particular point, right? So whenever it's used. So we will have corruptions if we don't do this properly. Sampler. So what do we do for sampler? We will ask for a sampler when we do vk create texture. And actually I'll do two versions of this because the second version will be a part of deprecated July 2025. Because I want to remove this because it shouldn't be using a vk sampler directly. Okay. Like in an ideal world, this should not be using a vk sampler automatically. And this we will not use at all for now. So you can comment it. And it's left commented deliberately. vk sampler. And then we can just pass that sampler in. So sampler goes in there. So descriptor image info is gotten from there. Descriptor image info is passed here. Descriptor write is writing to the descriptor set from here. Now, in a proper system, we would want to do batch all writes. We would want to batch all of these writes together and then do all of them all at once, once per frame, let's say, instead of having it write the descriptor every single time. But for now, we'll use this. Okay. So what next? So this will write to the descriptor. So now the descriptor has also been written to. We don't really have to worry about it anymore. So let's say the texture is being written as well, which we have created. So 1 second. Where do we write to the texture? We write it somewhere in this. No, I think we do it in the global memory itself. Sorry. My head is all over the place. I think we do it somewhere in app init itself. So nope, it's not here. So where is it? Create entity. Okay, we do it in create entity where we load the texture. Right, so you can see we've created a sampler there. We do all of this, we create the sampler, the allocations to write all of that into the texture. Create texture is no longer a valid one because it needs the sampler to work. So we'll just paste the sampler before the texture. Okay. And we'll pass the sampler in here. So the sampler will get bound with the create texture itself. Currently, we don't have to worry about the ownership and everything because sampler is owned by the material and the texture is also owned by the material. So the material will appropriately delete both of these. So let's continue on. One thing that we do have as an issue at the moment here is we can't destroy textures. So once a texture has been written to, it's more or less permanent, which means if I take a texture ID, like an RID, and I give it to the graphics card after the RID has been freed, that will crash the GPU. So Bindless gives you a lot of power, but with great power comes great responsibility. And that means my GPU will directly crash if I make a mistake. Okay. Anyway, so moving on, we have created the texture. So at some point, I'll have to pay the debt, and I will have to manually, solve all of this, debug all of this whenever I find the bugs. Now, texture has been created. It's already lodged or written to with the sampler, which means if I have a sampler creation here, that's not the sampler. That's not the sampler either. Yeah, here. So we create a descriptor set for the material where we write the texture view and we update the descriptor set. So this we don't need anymore. All of this is automatically handled by the bindless system now. So again, inside material, we don't need the descriptor set anymore. Cool. What next? So we build it again. It will give us a few errors because descriptor set is not a part of material. Instead, this whole thing can move right under the pipeline. Okay. So next thing we need to do is in miscellaneous data. This is not the part of miscellaneous data I want to look at. But okay, first of all, this descriptor set layout will reduce to a single descriptor set layout because it only needs to handle the uniform buffer. The other descriptor set layout, the one for bindless, is being handled by the texture manager, right? So inside init, we'll have a few issues, like it will tell us, okay, hey, you haven't done this. So material descriptor binding is gone. Material descriptor binding is gone. It's only a single descriptor set layout now. But in pipeline create info, we still have two descriptor sets. So why is that? So here we will actually have an std array. Let's say we don't want that. So calls descriptor set layouts equals. So second descriptor set will be the one from this one. And the first descriptor set will be render device. So I think render device. We do take render device here. So it's render device directly. Dot. And we want the descriptor set from this. So we want to first go to texture manager. Then from here, we want the descriptor set. So get, it's even going to just be descriptor layout, not set. Or the descriptor layout. So this doesn't exist. We'll create the member function. It will return a vk descriptor set layout. Wow, that was sad. There we go. So do create the descriptor set layout. Not create, return. Return M descriptor set layout. Okay. And this can be const, so we'll make it const. And in this particular case, it is proper const. Should be marked as count. Fine. Descriptor set layout. Okay. Coming back to particular thing. What do we do here? So we create, I have the descriptor set layout. We'll return this. This is great. Set layouts. Okay. That's it, right? Pipeline will automatically work for itself. Let's see what errors we have now. Miscellaneous data has padding due to alignment. Yeah, but it was padded how many bytes? Okay, entity manager has an issue because the script is set layout 1, which is consumed by entity, doesn't work because it just takes one layout now. In reality, it shouldn't even need that layout anymore, since we don't use that system for layouts. Okay, so create entity. We don't take those anymore. Remove the descriptor pool dependency. There we go. And that is create entity. Okay, let's see what else we need to do. Entity declared undefined descriptor set. Yeah, so this is, we've already taken it outside. So here, instead of taking it from anywhere else, we want to take it from texture manager. Descriptor. We want the descriptor set here, not layout. Okay, so we go in there, create the member function. It is a descriptor set. No discard. Const. And one thing I'm going to do is I'm going to make these pass by constant reference. And the reason for that is so that I can take the address to these, because otherwise they're L values and we cannot take addresses of L values without non-standard usage of C++. So return M descriptor set. Okay, what now? So go back here, it takes a descriptor set count, descriptor set, it binds it. Where's the uniform buffer one? So that is this one. This is also per frame, so this one should also bind itself. The difference is now the first set has reversed because the bindless descriptor set is less often. So it's updated less often than the camera descriptor set. In reality, both of them are roughly the same amount of updates. Okay. But, we still will ensure that things are nicely set up. All right. So with this, we should be able to render the material if we knew the index for the material. So that is a key point, like if we knew the index for the material. We don't have that. Like the graphics card, the GPU shader currently does not know what the index is for the material. So here I will say UN32T, but so that's actually not material, but more of a texture index. And similarly here, this is binding 00 and camera is 10 now. All right. Instead of being a texture, it is an array of textures. So this is more or less an infinite array. I mean, it's infinite on GPU side. In reality, it is set up from the CPU. And so, we have to do the bound checking. GPU doesn't help us here anymore. This will not work because descriptor indexing is a feature that we need that we haven't set up yet. But that we can get to soon. Mesh slang custom build is failed because sample is not a part of this. So here we will have to say something like PCB.textureIndex We will actually need to index inside the array, okay, to get that. And now, what's the issue with this? Cannot convert from, yeah, descriptor set allocate info. There's one more here, which is both descriptor set layout instructions have to be replaced by single descriptor set layout instruction. And this reminds me, inside texture manager, we did not destroy the descriptor pool and descriptor set. So at the end of a texture manager, so inside the destroy function, right? Once all the textures have been destroyed, we also want to destroy the descriptor set layouts and stuff. So first, we want to destroy the descriptor set that we don't have to do because it's a part of the pool. We can destroy descriptor pool. So render device. We don't have render device set up here. So we'll do that. Render device and render device equals start p render device. Assert MP render device. Right? So once we take the reference, life will be simpler. And device dot device descriptor pool is m descriptor pool and callbacks are null. As this we have to take. So we take from here. Then after descriptor pool, we have to do descriptor set layout. So we take the set layout and here destroy descriptor set layout. All right. So that should do it. Should destroy everything. We'll just set descriptor set to null here. Okay. Resolution. Any other issues? No. So far, so good. What has changed, however, is inside the shader, we ask for another PCB location, the uint32 for texture index. And this is something we haven't written in the PCB data. So first, inside the pipeline creation itself, we need to change this. So where's pipeline creation? Push constant layout. So push constant range. Size of XML matrix plus size of uint32t. Yes, I could write 4, but better to be perfect. So that's push constant range. Build again. This will give us a little bit of a validation issue because we wouldn't have written it here. So we will push the push constant. Which push constant is this? So first, the offset is the size of world transform. And the actual data is size of, and we have to take the size of what exactly? So we have to take the size of the index, which is a part of the texture itself. So entity dot material dot texture dot, so this is the index in and of itself. And entity dot material dot texture is the data that we need to pass, of course, a reference to it. So this will pass the texture. Note, this will pass the texture with the generation index. That's something that will throw off the shader. So inside the shader, we also need to get the index out. One nice thing about slang is you can have methods. So get, just call it texture index. And we call this texture ID instead. So we can say texture index. So I think there's a thing called property. You enter your texture index, get. So yeah, this is similar to C# for those who know C#. Okay, it's just that. Get returns texture ID, and index. Mask, which you have to copy from the CPU side. So inside texture manager, we have the index mask as a constant. We have to copy this onto the GPU side. So first expression u and index mask equals not sure how the slide constants work. Slide combine time constants. So these are link time constants. That's a different thing. Slide shader slide const expression. Let's see, that's a thing. Okay, it does have a const expression, so that's nice. Implementation of const expression was never completed. Fine. We'll go the C route. I shall define. Okay. Dual solution. All right. And texture index will just work because it's a property. Let's run it. Voila. There's a validation error here. So runtime descriptor array was declared, but the requirements was not set. We have bindless textures. So you see, we did not take a texture directly from like a descriptor data. So we don't have textures as a per object binding. It's bound once and it automatically works. Let's try something else. So just to ensure that this is working with more than one objects, we can go to the CPP where we are creating the entities at the top. So somewhere around there. Okay. What we can say is if I is greater than 0, we'll change the texture file. So I greater than 0. We're going to use the ternary operator here. We have assets, textures. There's the other one, which is container2.jpg. Okay, and we run this. Okay, can't open. It's literally can't F open. So container2.jpg is not available because it's actually a PNG file. That's a silly one. There we go. Right? So we just use texture indexing now, and it is just working. That's bindless textures right there. Turn it off, and there is no new errors. So the only error is it doesn't have the compile. So the compile time indexing thing that we can set up by saying, say not compile, runtime indexing. So that we can set up by going to the render device. Here, when we ask for features, so we ask for features in this. What we haven't done is we haven't asked for the specific feature that allows us bindless. Vulkan 12 features, const expression. It actually won't be const expression anymore. Just const. And to be fair, it can be const expression, but it's not worth it. Const features 12 equals that. VK structure type physical device worker 1 2 features. The next is and a physical so features 1 3, right? Sampler mirror clamp to edge. Okay, let's see now. We don't need that. Draw indirect count. We will eventually need, but we don't need that right now. We don't need that, don't need that, don't need that. Shader buffer int 60. We don't need that, don't need that. Don't. Descriptor indexing, true. So we do need that. Dynamic indexing. Runtime descriptor array, true. Descriptor indexing is true. Hold on. So it asks for runtime descriptor, but it did not ask for descriptor indexing. Why? So this allows us to have. So descriptors that are not used by any pending command buffers can be updated, which enables writing new descriptors for frame n+1 while frame n is executed. Okay. So this we currently don't have because we're not loading textures while the system is running. But once we have that, we will need this. Dynamic indexing. So we will need these. So I'm going to add these. So input attachment, I don't care. Uniform textile buffers, I don't care. Uniform buffer array, don't care. Sampled image array, this I do care. Storage buffer array, don't use it. Storage image array, we will use it. So that I'll add already. We don't use input, don't use textile buffers. Uniform buffer update after bind. True, because this allows us to update the uniform buffer after it's been bound. Sampled image update after bind. True. Storage image update after bind. True. Storage buffer update after bind. We won't be binding storage buffers. We won't be binding textile buffers. Update unused while pending. True. Partially bound. True. Variable descriptor count. Wait, I don't think we're using this one, but we can check what this is. So bits can be set in each of the descriptor set layout binding flag create info, specifying options, but okay. Variable descriptor count specifies a variable size descriptor binding whose size is only specified when the descriptor set is allocated using this layout. Allow descriptor count is used as an upper bound for the size of the descriptor. Lies used only for the last binding of descriptor setting. Okay, we can leave that in. We don't care about these. We'll use this soon, but I'm not adding it right now. Okay. So that should be fine. And here, instead of taking 13, we'll take 12. What's wrong with this? Void pointer cannot be initialized to it. Excuse me, what? Okay, because this is a const. This expects a non-const void pointer. That was the issue. All right. So this is it for now. Okay. We are not adding any other extensions. If we build solution here, that's fine. The few things we have missed in the creation here. So when we created the descriptor set layout, there should have been a few, not this thing, not the layout here, but the create info flags. We create descriptor flag partially bound. We create descriptor flag update after bind bit. Create descriptor flag hold on. This is flag for descriptor layout binding. Interesting. Descriptor binding flag created descriptor set layout bindings. At layout bindings, binding count, binding flags. It's a part of descriptor indexing. That's Vulkan 1.2. Okay, so we do need to add this now. So first bindless binding That sounds like an oxymoron, but that's life. Eh? So S type is VK, structure type, descriptor set, layout, binding, flags, create info, in external pointer, binding count is 1, binding flags. Okay. And here in the pnext, we'll pass bindless binding. I'll have to resource this again, I guess. VK, binding, flag. So the binding flags equals. That's not a struct, is it? The descriptor binding partially bound. VK descriptor binding update after bind. VK descriptor binding update after bind is done. Update unused while pending. Okay. Even though we support that feature, we won't probably use it, the one with variable binding counts. So we don't actually need it. Okay, what's wrong with this? Because update after bind bit. If update after bind bit is set, then update after bind pool bit must be set. So in the descriptor pool, we need to set that. So set layout, pool size, flags, VK, update after bind. After bind descriptor set layout, create update bind pool bit. What? What? That set layout create flag bits. Update after bind pool bit is a part of descriptor set layout create flags. So it's actually here. That's interesting. I'm not sure that would just work with the pool, would it? No, there. So set layouts is created with update after bind pool bit, but the descriptor pool was created with no flags. So yeah, pool also needs its relevant flags. Descriptor pool flag create update after bind bit. Okay, no errors now. So that looks fine. Relatively short requirement compared to my average because we've done less than 1 hour, but this was part 2 of bindless textures. So yeah, we have more or less some semblance of bindless texture working. We will need to, however, verify this because Vulkan is a complex thing. So Vulkan, bindless, and we can read a blog online, why not, right? So let's see it in the vulcanized thing itself. So what do we need? Immutable samplers, because that's what we're doing, but we don't care. Mutable descriptor type, descriptor buffer. Hello. So descriptor pool requires period and down. Descriptor count is set to an upper bound. You don't care for that. A single descriptor set layout and pipeline layouts are used for all pipelines. Each descriptor set contains period and maximum amount of that specific type. Immutable samplers are used to learn about bounding itself. No, this is not it. I mean, this is a good content, but it's not the thing I'm looking for. I'm looking for any flags I will need. So update after bind is something I've done there. So binding flags that you have to pass in. We did that. Okay, so it seems for now we are fine. But while we are here, let's do a little bit of additional work. Okay, so struct ID, or call it our ID, right? And this is slang. So one of the nice features of slang, some of the nice features of slang, there's actually a law. So this is not C. This I can almost call it resource, which is data. Where was text? Where text? Given that I'm not actually making text, bindless dot slang. Location, I'll change it to assets, shaders, select folder, add. Okay, so we have this bindless.slang thing here. What I can do is I can create a nice little structure. So straw RID, okay, for a particular resource. So I can actually say RID of type T, where T is opaque descriptor. Yes, we actually support generics and interfaces on GPU now. Welcome to 2025, right? So that's RID. And RID will contain a event as an index or internal. We'll make this private. Yes, we have data hiding as well. Property, we wouldn't do that actually. Instead, we'll make property has value. We don't have anything to set has value, do we? So generation start with generation 0. And so null is always in null. Okay, start generation with generation 1. Let's go back on that particular thing. Let's always start generation with generation 1. Wasn't here. Where was it then? Inside the constructor of texture manager. So here, default generation is 1. Okay, it is 1. Generation default is 1. Okay, so I don't think I will fix it. I'll leave it as it is because this allows us to do some nice checking. So since default generation is 1, what is hey, is it real? What is real? I don't know what you're asking for, sir. Static, event, generation index. So generation mask equals index mask. Width const static. Event or static? Does it? It doesn't have that feature. On static event index mask equals 0x. So we have this number in the slang here. So we'll copy that. So again, const static generation mask is the leg of that. So good to go here. Okay. Then also private property has property bool has value get return index mask greater than 0. Okay, so I'm going to do a little trick in order to ensure that at any point of time, if you can use a handle, the handle is valid. You can do this by ensuring that the handles can never be copied. So for that, we go here in Excel Manager. The handles are created as our IDs. So you see we have the constructor that is default and available. It always leads to a null result, which we don't care about. But we can also say RID, so it's RID again, const and equals delete. So that's the copy constructor. It's been deleted. Operator equal to. So this is a copy assignment, also deleted. We will support move. So RID, and other. So the way move works is we will take the other.m index into our current index, and we'll set other.m index as 0. So that will set it to the null value, right? Similarly, we'll take RID other and operator equal to. So this is assignment. So we cannot do this construction thing that we've done here. Instead, other.m index is 0 is fine, but this dot m index equals other dot m index. Okay. Most is returning non-void, so it returns star this. And we'll also check if and so this equals and other, because if you just try to move itself into itself, we don't want to actually destroy itself, right? Because this would become assign self to self, then assign 0 to self. That would break things. So we'll set it like this. Move assignment should be marked no accept. So no accept it is. And similarly, this also becomes no accept. All right. Any other issues? No definition out of class code. Because that's the right thing to do. Our IDs will eventually be refactored out, but for now, we'll just use it here. Okay. Look, let's keep the original alignment. No copy, moves allowed. All right. So does that break anything in our code? It does break a lot of things. So inside Entity Manager, we try to move material, copy the material. That doesn't work. So material has to be moved in, because of that, this wouldn't work. So std move, specifically say it like that. Actually, this should be actually forward material. Yeah, that's better. There are others, so we'll look at those. No equal to such that it takes a texture ID, because texture ID, again, this is moving. So std move texture over there. So that moves itself. std move the material over here. That moves itself. Again, texture opt dot value tries to get this. So std move. Std move. Hold on 1 second. That doesn't work, because that will delete our texture, right? So what we need to do instead is this becomes const ampersand. The very thing we talked about doing yesterday. Take it by reference. Is valid should also take it by reference. Okay, our ID is a const ampersand. This cannot remove the const cast. So we can just cast it to a const pointer. Okay, what next? Dot texture again to free this. Now here there's a little bit of a different thing. So free texture, we deliberately do want fetch texture unchecked. Again, const ampersand. Const. So this is fine. But here in RID, we do want it to take it by F. Constant reference, we want it to be moved into this. And that way we know that the handle is taken care of, right? It's gotten rid of, let's say. So texture is taken here, this fetch texture. Okay. What we will do is we will take std move RID into some auto this thing, and that just destroys it. So it just assigns it to something that we don't care about. And at the end of this function, this RID is gotten rid of. One more problem here, which is memory hackery to create the texture ID cannot convert value of our texture ID to return type. That's because we haven't done a std move. Okay, so now this just has to be moved. There we go. By doing this, what we're effectively doing is at the end of this free texture, this texture is cleared. So there's no way you can have, like, after freeing it, there's no way you can keep this texture reference. All right. So coming back to mesh.slang, we take this index mask to get texture index. We also check property bool as value, get, and we just see if, oops, this is the wrong place. So we were actually working on this. So if index mask is greater than 0, is entirely a wrong thing. As value is based on internal and generation mask. We don't even need to bit shift it because being greater than 0, okay? You don't need to bit shift it because it specifically only takes the generation bits. And what we're trying to see here is the generation bit 0 or not. So if it's greater than 0, then we're fine, right? Because all the correct values have at least generation 1. Property bool value, not bool, uint value that should return something. So in this case, actually, we'll return t directly. So yeah, in here, we'll take the sampler 2D. We'll paste it up there. G textures, we'll call it. And when you try to take value, what the system will do is it will do a get like this. It will then index. So it will try to check if it has a value. And it will index. So to do check if has value, else place folder. I'm only writing this as a to-do because I don't have this set up right now. But it will take textures. Then it will put inside there internal and index mask. Okay. And it will return this. That's it. So it will try to return type T and found sampler 2D. Yeah, because, this is sampler 2D. I think the way to go with this is dynamic resource, dynamic resource kind, something like this, if I remember correctly. Slang, bindless. So there's a thing in slang, called diff. So it's called descriptor handle here. So descriptor handle is nice because it does this exact thing that I'm trying to implement here. And you can get it to directly index into a dynamic resource like this, kind of general. So what we want here is to the kind of sampler here. What we want is to get it to actually index into this dynamic resource and try to get the index mask. So you can see it sees if it's a spirv type. If it's a spirv type and if the resource kind is sampler, then it will take the thing and it will cast it to another descriptor type. So I'll add that too. And that works, right? So this will return the value as a descriptor, which can directly be used. Which is why they use descriptor handles for RIDs. The only reason I'm not using descriptor handle is because descriptor handle is uint2, is 64 bits, and our handles are 32 bits. So why waste extra 32 bits, right? So I'm implementing it on my own effectively. Similarly, there's an extension class. So extension T, I think it's like this, extension for T, where T is opaque descriptor, because you cannot extend interfaces directly. Or is it like this? Oh yeah. Yeah, because we need the generic parameter first. So now what we say is for IOPIC descriptor T's, we will add an extension, which all it does is has a public type alias where RID equals RID of type T. RID cannot have higher visibility than the extension because it's a public one. So we make this a public one as well. And this has to be public as well. So public, this is okay. Property has to be public, has value and value. There's a reason why I'm creating has value specifically in that main. So in mesh.slang, we can first import, it's a proper import bindless. And then inside here, we can actually just take, so this was what sampler 2d dot RID. Don't need that anymore. And here, instead of doing that, we can just say PCB dot texture. So we can check this. If let texture equals PCB dot texture. So here, if let syntax else something else, texture here, PCB dot texture ID is there. We'll copy that, paste it here. This will automatically work with the has value. So it will check if has value. If has value is true, it will assign texture. Else, it doesn't have anything. So we can safely use the other side. And we can say the value is directly just the interpolated colors, right? Build the solution. Let's see if this works or if it's buggy. Right, SDL, of course. Rebuild solution. Run it. Okay, this is working. It's just fine, right? -3, -2, -1, 0, 1, 2, 3. The number of items is also correct. Wait, did we see some issues with the frame rate? Let's keep it running. Still have 144 hertz. Nothing seems to be changing there. So I think we're okay. Huzzah. It's just fine. Bindless texture is done. And we even use the proper slang niceties to get it working. All right, then. This was it. I hope you enjoyed. Follow along for the next time. We'll implement bindless buffers and we'll get some vertex pulling done. Either that. So actually, not either. We will do the bindless. No, let's load the meshes first. Once we start loading meshes, we'll see some issues with the whole thing, and then we'll add the vertex buffers. All right. Thanks for joining in. Hope you enjoyed. And have a good rest of the day or have a good tomorrow. Cheers.